Dear colleagues and friends, it is my great pleasure to welcome you at IPMU 2002. It is my great pleasure to see you in presence, to see faces and not through screens as we did the last 2 years and a half. So we try to keep the conference as much as possible in presence. There will be a few exceptions with presentations online, but just very few exceptions. This also has a drawback, this reopening, since I would like at this point to have some institutional and boring talk by some important person at the university. But everyone seems to be abroad, so no way. But especially I've asked two friends of us, many of you knows very well, Gabriella Pasi, she is the vice rector and the head of our department. So she just told me to pass her greetings to every one of you. And she's now in Madrid attending another conference. And I take this occasion to give the first thanks of this conference, in particular to my university and to my department, who allowed me to organize the conference. And of course, to the executive committee of the conference. Bernadette is here, and Ronald, unfortunately, could not come. There will be, of course, other occasion to give other thanks to other organizing people, and I will do it later during the conference. I just now want to give some logistic and organization remark. So first of all, here I just put some important moments that will be at the conference, beside the presentations, of course. So this morning we will have the Campere Ferrier Award, just after Tommaso talk. And then on Tuesday we will have the Best Paper Awards. I know that the program committee chairs are working on this. And I recall also tomorrow evening the EOSFLAT meeting. I think everyone is invited, also if not member of EOSFLAT is invited to attend the meeting. But especially those who are member are invited to attend. Of course, there will be also social moments starting from this evening. And the cocktail will be here, perhaps just outside the room. I guess you have seen they are preparing everything for lunches and coffee breaks. Everything will be here. And the other rooms where the other presentations will be are on the same floor, just the other side of the floor. And of course, there will be the dinner on Wednesday, and before, for those who are enough brave to stand with 40 degrees in these days, can enjoy the guided tour. Let me just give an explanation of why you don't have found the programs, no book of abstracts, but only the e-book of abstracts, and only those who explicitly ask for the printed books got them. It's just for to save paper. That's the main reason why we did this. So someone, I understand, may be disappointed, but this is our motivation. And in case you need some help or you need some information, of course, you know very well the website. You can ask to the staff you met at the registration. And there is some people from our university who you can ask something from the university, from the Logistic or Milano point of view. I just put here their name. I guess some of you know some of them. And there is also a Twitter account. It is not much used, but if you want to share something, you are welcome to do it. So I think that's all for the moment. And we can now, I can now leave the floor to Bernadette and then to Tommaso Poccio for the keynote lecture, our first keynote lecture. So welcome again and enjoy the conference.
morning. First of all, I would like to express my thanks to Davide for the hard work he has done. And I would like also to express my thanks to the program committee chairs, Ines Cuso and Jesus Medina Moreno, Dominique Slezak. They have done big work also because of the small amount of submissions and the high level of quality that we want to keep. And so the special session chair was Celia da Costa Pereira, the publication chair Davide Petuiti, the virtual conference chair Rafael Penalozza, the web chair Marco Viviani. So I would like to thank all of them for participating in the organization. My thanks go also to the special session organizers. Many thanks to them and to the viewers, to the program committee members, to all those who participated in the success of the conference. So many thanks to all of them. So it's now my pleasure to introduce the first plenary lecturer. Tommaso Poggio is the Eugene McDermott Professor in the MIT Department of Brain and Cognitive Sciences and the Director of the NSF Center for Brains, Minds, and Machines at MIT. He is a physicist whose research has always been between brains and computers. He is now focused on the mathematics of deep learning and on the computational neuroscience of the visual cortex. He was involved in starting or investing in several successful high-tech companies. He received many awards for his multidisciplinary work, and it would be very long to give a long list of all his achievements. So we are very happy that he accepted our invitation to give a lecture today. The title is Science and Engineering of Intelligence. Please join me in welcoming him with a round of applause.
So it's great to be here. Thank you to David and Bernadette for the introductions and for organizing this great symposium. I would like to speak with you about the science and engineering of intelligence. We are living in a couple of magic decades in which artificial intelligence has made very significant advances, starting about 2 or so decades ago. We have now machines that are closing to humans in terms of understanding vision and speech, and the transformers are as good as an average human programmer. They probably still lack a sense of self. They still lack awareness, self-awareness, consciousness, but we are getting there. And when we started this Center for Brains, Minds, and Machines in 2013 with funding from the National Science Foundation, and I say we because it's a number of people at MIT, Harvard, and other places. My main partner in this was Josh Tenenbaum, who's faculty at MIT. The focus of the center was and still is about the problem of intelligence. And I think that the problem of intelligence is one of the great problems in science, like the origin of the universe or the origin of life or the structure of time and matter. Personally, I think it's the greatest one, the greatest of all, because if you can solve it or make progress in it, then you can more easily solve all other great problems. So that's why. And we started this center in a tradition that stretches back at MIT at least 50 more years, starting with people like Marvin Minsky and Noam Chomsky and Claude Shannon. So what we wanted is to have raise a generation of young researchers that could know interdisciplinary sciences, in particular cognitive science, neuroscience, and above all, computer science and machine learning. So we wanted to have the science and engineering of intelligence, understanding how the brain works, that's the science, that's neuroscience and cognitive science, and developing machines that could replicate some of these abilities, that's the engineering part. And I'm using science and engineering in the classical sense. For instance, a good friend of mine, Francis Crick, who is on the right of these pictures, taken in the Bodego Desert in Southern California quite a few years ago. He insisted that science are all the disciplines that studies nature, like chemistry and physics and biology and astronomy. And engineering studies human artifacts, including mathematics, perhaps. It's an open question whether mathematics is science or engineering, whether you are discovering or inventing. So engineering is no less basic research than science. It's just different object of research. And in the center, we are doing a quite successful educational efforts in trying to create a new generation of scientists that are fluent in the engineering and the science of intelligence. We have a Brains, Minds and Machines summer course in Woods Hole at Cape Cod, typically in August, 3 weeks, in which we have actually, I think, succeeded in forming a community of young researchers that are expert and fluent in these different disciplines. If you are interested, this is a great course, apply in time, it's quite selective. Now, in the center, just to show that science is coupled with intelligence, we have as partners universities and research institutes like the Max Planck Society and the Weizmann Institute, but also the typical actors you may imagine on the business side, like Microsoft and Google. And we started having partnered a couple of small startups like DeepMind and Mobileye. We started from students and postdocs of mine, which in the meantime have become pretty large and have been acquired, DeepMind by Intel, DeepMind by Google, and Mobileye by Intel. So the question is, how can we solve the problem of intelligence? And intelligence, human intelligence, how it is realized in the brain. And how do we replicate it in machines? Where the next breakthrough is going to happen? And in 2013, the obvious intuition was that several of the next breakthrough will come from neuroscience because the key ones had come from neuroscience. As a demonstration of what I'm saying, let's look at 2 success stories in artificial intelligence, 2 recent ones, the ones I mentioned, DeepMind on the left, Demis Hassabis is the founder, and Mobileye on the right. Amnon Shashua is the founder. They are both members of the advisory committee of CBMM, in addition to other great people. And the two connections are that both DeepMind and Mobileye rely on algorithms that come ultimately from neuroscience. DeepMind developed the first AI system, AlphaGo, that beat human champions at the game of Go. And in the meantime, have systems like AlphaZero that can learn how to play either chess or Go or other games better than humans in a very brief time, playing against themselves. So they have essentially solved the problem of intelligence, have beaten humans in the virtual world of games. And most of their algorithms are heavily dependent on reinforcement learning. On the other hand, Mobileye is a leader in autonomous driving. The first few years, Tesla has had their system from Mobileye for autonomous driving in the car until we fired Elon Musk. I said because I was member of the committee of the board of Mobileye who took this decision because he was not careful enough in advertising the risks of autopilot in Tesla, saying that he should have said it is not really an autopilot. Anyway, they have the best systems for autonomous driving and selling them in cars from Volkswagen to Toyota to Audi and so on. And they rely on deep learning, and reinforcement learning. So reinforcement learning and deep learning, as I said, came from neuroscience. Reinforcement learning has a long history going back to Pavlov, at least, and conditioned reflexes. And deep learning, as an idea, starts with the work of Huber and Wiesel at Harvard in the late 50s, early 60s, which prompted them to describe the architecture of visual cortex as a hierarchical network of layers composed of simple and complex cells, and they said the hyper-complex cells, an architecture which is very, very similar to the ones of most deep networks this day, especially convolutional networks that have been doing most of the work until transformers came around, and I will speak about transformer in a little while. So, these are success stories in AI showing that neuroscience had an impact in suggesting the core of the algorithm they've been using. And by the way, this is an interesting parenthetical remark I want to make. This is a video from '95. We installed in a Mercedes of the research group of Daimler-Benz one of the very first learning algorithms for machine vision. It was trained with a few hundred photos to detect pedestrians. Now, the point I want to make is that at the time, in '95, we were very happy about the success of this. It was making a mistake, one mistake every 10 frames, which we thought was great at the time. This is more than 25 years ago. As you can see, you see some mistake like the traffic light being detected as a pedestrian. So it was one error every 10 frames, but it was 3 errors per second. So it was perhaps successful scientifically, but in terms of application, completely useless. today, a similar problem by the system of Mobileye, they have one error every, I don't know, 150,000 kilometers of driving. If you make a back-of-the-envelope calculation, this means that accuracy in these 25 years or so has improved more than 1 million times. It's doubling accuracy every year for 25 years. This is a kind of Moore law for machine learning. That's why machine learning has become usable in many applications, from Alexa to autonomous driving. Okay. Now, the story from 2013 is interesting. There has been less of a contribution from neuroscience. Engineers have made a lot of progress without real suggestion from the sciences of the brain. But before that, another trend is that applications are well ahead of theory, and will come back to this later. In other words, we have systems that work well, deep networks that perform pretty well, but we still don't quite understand the theory underlying it and why they work as well as they do. Of course, this happened before. Electricity. Alessandro Volta. Alessandro Volta was a professor in Pavia, who is not far from Milan, 30 kilometers or so. He published his first explanation of the battery, of the pila, in the year 1800. It was made a count by Napoleon. If you think about it, people don't realize it. This was a very transformative invention in the history of mankind. Until 1800, information traveled at the speed of a horse. After the battery, the invention of the battery, information has been traveling at the speed of light. Alessandro Volta himself had designed a telegraph line between Milano and Pavia, which was never built. But the other interesting thing, which is relevant for the question of machine learning, is that there were a lot of applications after Volta, immediately after Volta, including electrochemistry, telegraph, and so on, without people really understanding what electricity was at the time, or the theory behind it. The invention of the battery itself was kind of a random event. And it's only after Maxwell, 1860 or so, that the full power of electricity, including radio and computers and the internet and eventually AI and machine learning, came about. So theory can be important, and it's not always the case, actually the opposite, that the main discoveries follow from the theory. It's the opposite. Okay. In a similar way, as I said, the neuroscience contribution to artificial intelligence, not to neuroscience, had less impact in the last 8 years or so than earlier on. But of course, this may change. Interestingly, in the last advisory committee that we had of the CBMM, or the Center for Brains, Minds and Machines, Demis said that until a couple of years ago, he had thought that in order to build a real artificial intelligence system at the level of humans, you'd have needed neuroscience. And at the time of the meeting, he said maybe with 90% probability, we'll not need actually neuroscience for building intelligent machines. And so the question is, if you are interested in neuroscience, because you are interested in understanding the human brain, as I am, then of course you should do not only computer science, but also neuroscience. But if you're interested only in building intelligent machines, should you be interested in neuroscience or not? And I think you should be interested in neuroscience. The reasons is, of course, that the big prize in terms of understanding is understanding human intelligence, and so for that you need a neuroscience, but also that the engineering by itself without neuroscience has made a lot of progress the last 5 years, but it may hit a wall at some point about the capabilities that machines don't have yet, like self-awareness. And then what? Then neuroscience may be what allow the next quantum jump. And furthermore, at some point, it may be important to connect our brain to machines, to expand its capabilities, to connect it to the internet. This, by the way, this is half a joke, but this may be the only way to live forever, and maybe the only way to travel to the star, and if we connect ourselves to machines. So forget Elon Musk Mars projects. Okay, so the science engineering intelligence, it's a great interdisciplinary revolution, for sure, that is touching and transforming already all sciences and a lot of disciplines in engineering. And what I want to do next is something a bit more formal and quantitative, try to give you some idea where we stand in understanding why these networks, deep networks, work as well as they do. And maybe understanding this will give us some cues also in understanding how the brain works. So there are many different architectures developed over the last 10 years, starting with convolutional deep networks on the extreme left. It's a caricature of them, but essentially they implement this locally hierarchical architecture that Hubel and Wiesel described in the visual cortex of the monkey. But then in recent years, the last 4 or 5 years, there are other architectures like transformers and similar one like MLPs and perceivers and so on that also do very well, especially non-vision domains like language in terms of learning and producing language. So why all of these things work so well? Are there some common principles? Okay, so I'll try to answer this question, and some answers are clear, some others would be more conjectures. According to the three parts of learning theory, which are approximation theory, optimization, and generalization. So approximation is how can a network approximate an arbitrary function, so a task you are trying to learn, an input-output function. It's a question of representational power. What is the representational power of these deep networks? The learning theory part about generalization is when you achieve zero error or very small error on the training set, why does the network generalize, do well on other examples that are not in the training set? And finally, the optimization part, how can you learn on the training set, so reduce the error, do the optimization, because the optimization problem involved is very large, in principle, very, very difficult. First of all, I'm sure you all know, but a deep network, I consider first a deep a network like a convolutional network or a dense network, is composed of several layers of units. Each unit is so-called a neuron. A neuron is a caricature of a real neuron. It's just an RLU, a function shown on the right, that receives a weighted sum of inputs. And so the weighted sum is a number. If this number is smaller than 0, it's set to 0. Otherwise, it's set to the number itself. That's the RLU function. I don't include biases because, in effect, they are not really needed to achieve good performance. And so the key here is how to set the weights. And the weights are found by optimizing, so minimizing the error, like the square error or the cross entropy error on a training set of capital N training pairs, XY pair, where the XI are the input vectors like images, and the YI are the output, like labels, for instance. In binary classification, would be +1, -1. And in this minimization, you are trying to set weights that minimize the error, cumulative error across the whole training set. And you're doing that by using typically gradient descent techniques in which you are try to find the minima of the loss function by following the gradient. And the most used technique is stochastic gradient descent, which instead of taking all the data for each iteration of gradient descent takes only a random subset of the data at each iteration, a random subset called mini-batch. Okay, so I think the key to, and this is a very personal view that I'm not sure anybody else shares, but the key is given by approximation theory. Why all these systems work. So let's go to approximation theory. And an old result that was well known since the 80s, and it's partly the reason why in the 80s people focused on one-layer networks as opposed to deep networks, is that both one-layer and multiple-layer networks are universal approximators. They are like polynomials. They can approximate any continuous function on a compact domain arbitrarily well. Okay, so there is no advantage from this point of view in using a deep network instead than a one-layer network, like, say, a kernel machines. So they both can represent, approximate any continuous function. Okay, however, there is a well-known curse of dimensionality in approximation theory, which is that the upper bound on the number of parameters you need to approximate a function of d variables is exponential in d. More precisely, suppose you have a function of d variables and of smoothness m, for instance, Sobolev space with smoothness m, but m is not so important. It's a measure of smoothness. Put it to 1 for now, and so the number of parameters you may need is bounded by the error you want to, the maximum error you want to have, epsilon, and the dimensionality d's. If I want an error of 10% and I have d equal 8, then I have a number of parameters that is upper bounded by 10 to the 8, okay? And if instead of 8, I have, say, as many variables as pixels in CIFAR images, which are small images, 28 by 28, then I have around 10 to the 1,000 in this bound, which is a lot. So this is a real problem. That's why it's called curse of dimensionality. One way around is to consider very smooth functions, but you may not have the freedom to choose. The other one is to make an assumption about function, to assume that the function is a function of functions. It's a compositional functions. What you see, let me see. What you see, oops. What you see, no, okay. So what you see in the figure, you see in the figures on the right, top right, are graphs of function. On the first one on the left is a generic function, you don't know much. But the one on the right tells you this, each right dot is a constituent function, like the equations on the left is a g, is a function that depends only on two variables. So you can see that, for instance, this is just an example, but through a function graph, which is a binary tree, you can build a function of as many variables as you want, made up of constituent functions that are functions, each one of just two variables, okay? So what it turns out is that if you have compositional functions like this one, then and you try to approximate through a deep network with a similar architecture to the graph of the function, then you avoid the curse of dimensionality. Because of the theorem there that we proved with Rushikesh-Maskar a few years ago, that basically says that for a compositional function, what determines the curse of dimensionality is not the number of variables of the whole function, but the number of variables of the constituent function that have the largest dimensionality. Okay, that's interesting for many reasons, one of which I'll tell you at the end. So let's make this assumption that functions are compositional. And the proof, by the way, is simple. It's just one page. I'll go into it if anybody's interested, but for now, just the message is that you can prove you don't have curse of dimensionality. And this result can be extended from binary trees to more complex directed acyclic graphs representing a function, like the graph on the right, for instance. And as I said, you don't need to read this long theorem, but the key point is that the effect of dimensionality is not the total number of variables, but is essentially the number of variables in the node in the graph which has most inputs. That's what sets the bound on the number of parameters. Okay, so there are a few comments here that for a given function that admit a compositional graph, the graph is not unique. There may be other ways to compose the function, and several caveats of this type, but many functions that you encounter are compositional. And then this also brings up an interesting point, is that if you have functions that are compositional, like basically for convolutional networks, the network structure reproduce the assumption you're making about the underlying function. This for an image means that you don't have to process all the pixels at once of the image, the bottom left to the top right. You can just look at small patches in the image, process them together, and then do the same at various levels. And it's the same for text. You don't need to recognize, in order to recognize the meaning of a sentence, to read, process all letters at the same time. You can first parse the words, recognize single words, and then put together the words in sentences and the sentences in paragraphs. So a lot of things are compositional just in nature and in human artifacts like text or speech. And so for compositional representation, it's empirically and theoretically clear, I'm just stating this, that if you can optimize, then you can also solve at the same time the machine learning, the generalization problem, and the approximation problem. What is not obvious is that you can do that in the case in which you have more parameters than data, training data, which is typical for deep networks these days. It's not clear whether optimization can find when you have more parameters than data, can find the function that minimize the training set error, and at the same time find the function that has the least complexity. This is what you need. Now I can tell you that, in fact, that's possible, and that's very recent unpublished work. So you have here a deep network shown in two versions, one in which you have weight matrices split in terms of, instead of calling them W1, W2, I'm splitting them in V1 and rho 1, where V1 is a matrix with unit Frobenius norm, and rho 1 is the norm of the original W1 matrix. And I can represent that network. So that's a rewriting of the standard network, where you have these matrices and then RLU functions in between. And on the right is another rewriting of the same network, in which now I've collected all the rho 1, rho 2, and so on, as their product rho. And this is possible because the RLU function is homogeneous. So the RLU of AX is the same as A RLU of X. And this allows this rewriting. Okay, then you can write the gradient descent equation in terms not of W, but of rho and the VK, the normalized matrices, the equation on the bottom right. And these are the gradient descent equations, and from this you can derive convergence value for rho and for V. And for rho, you see that there is a value of convergence at which, this is in the case of binary classification, so interpolation here, which is essentially guaranteed if you have more parameters than data. So you have the ability to interpolate, and with weight decay or regularization parameter lambda in the row equation, you get quasi-interpolation. So you get to +1 and -1 within an epsilon, which depends on the value of lambda. And you can show that you have a bias in this equation for the smallest possible row. You cannot a priori, because this depends on the data, say what is the smallest row, but the gradient descent equation will tend to converge to this smallest row. It's not guaranteed they can, but it will be one of the smallest row. If you do experiments, you see that rho grows from 0 because of initialization to close to 0 to some value. This is the blue line. And at the same time, the training error, the green one, goes to 0, and the test error, the red one, goes to some pretty good value, like, I don't know, 5% error or so. This is on CIFAR images. These are training with, because it's binary classification, on 10,000 training images and testing on 20,000. Now, how does this explain generalization? It explains generalization because there are some old bounds that tells you that the difference between the expected error, the error you're doing on future data point that you have not seen before, minus the error you're doing on the training set, which may be 0 if you're interpolating, that is bounded by a term which is the Rademacher complexity of your network divided by a margin which is 1 in our case because it's a binary classification and essentially interpolatory binary classification plus some log term. And the key part is that in our network we have that this the Rademacher complexity term can be rewritten as rho, which is, as I said, the product of the Frobenius norm, time the Rademacher complexity of your network with normalized matrices, divided by square root of n. And so you have a bound that can be written as 2 rho over square root of n, where we bound the Rademacher complexity of the unitary network as 1. That's not necessarily a good bound, but certainly an allowed one, a correct one. And so if we use this, we can see that we can have a good generalization error, even if you are interpolating, even if we have more parameters than data. A correct prediction of this is that smaller rho will give you better expected error. And in order to achieve this, we added label noise to the CIFAR data and did our experiments again. And we see that by adding noise, we get larger and larger rho. Therefore, smaller 1 over rho, which is the margin. And at the same time, by adding this label noise, we also get, as intuitively expected, worse error, expected error. And so this is, the prediction is verified, that if we have larger rho, we get worse error. And even in absolute terms, we get that the prediction in terms of this upper bound is still far out. You know, you have a number like 34 or 10 instead of, and they should be number between 0 and 1. but there's much, much better than what you would get from bounds like the ones given by VC dimensions, where you will get, typically in this case, in the order of numbers like 1 million or so as a bound. So that's much better. And in fact, recently with a very similar network with a reduced number of parameters, which still are more than 200,000, we get numbers in terms of our bound that are much closer. You see on the rightmost column of the table, much closer to the actual expected error. So this is a demonstration that something that people have described as an open problem. How can network interpolate the data, have so many parameters, they interpolate the training data, but at the same time they generalize? How is that possible? And this is exactly how is it possible. You can have a lot of parameters and interpolation and still reasonable, good expected error, and the bounds based on rho give you essentially good insight that controlling rho is the key part in ensuring generalization. So over-parameterization and generalization are not contradictory, and this, I'm not saying this solves completely the problem, because I think the bound can be improved by improving how we bound the Rademacher number of the unit network. That number will depend on the architecture, and empirical evidence suggests that having a smaller number of parameters in the architecture will improve that bound. So there is more work to be done there, but we know the direction. And so the summary at this point of the situation is that if you have networks like deep networks that are trying to learn a compositional function, then everything seems to work. As I said, there is work to be done, but you can explain representational issues, generalization, optimization. But what about transformers? Now, in transformers, the problem is you don't have a graph represented by a convolutional network that you assume or is correct for the underlying function. You just don't know. You are looking at a sequence of tokens that may represent words or pixels, and you don't assume anything there. In transformers, you have this first step called self-attention. And here is a conjecture. The conjecture is that what transformers do is they don't know what the underlying graph is, but they assume that the function, the underlying function, depends on a sparse number of variables. So not on all tokens of a sequence, but only on some of them. And then they try to find which one by a recursive application of a sparsity-inducing algorithm. That's conjecture. There is more that I hope I can tell you in a few weeks or months, but for now that's a conjecture. And so at this point, it's an open question. Now, I should finish here. I just want to add one interesting point, which also, preliminary work, but is the claim, I made at the beginning this assumption that functions that you are trying to learn are compositional. This seemed, when I first did it in 5 or 6 years ago, I thought this was a quite restrictive assumption. Maybe true for images, maybe true for text, but not necessarily for many other problems. It's an hypothesis about the word. It has nothing to do with networks, right? So, but in the meantime, I think the following may be true, is that most functions of interest are compositional. And I don't know what the statement will be in its final form, but there is a definition, classical definition, going back to Church and Turing, about effectively computable functions. Basically, any function that a Turing machine can compute with. Now, one could define something like an efficiently computable function. A function, one possibility, I'm sure there is a better, more general definition, is that if it can be, it's a function that can be computed and stored in, or stored in memory that is, or a number of computation that is most polynomial in D, in the number of variables, not exponential. And, you know, the proof is something like this. It's not a serious proof. It's kind of a joke, but is that if you have D large enough, then you have, for instance, 1,000 small images, like cipher, then this would require incredibly large memory. Think that we have 10 to the 80 protons in the universe, right? So here we have a number which is much larger. So functions of this type are not storable, cannot be stored. You cannot have a table with 1,000 dimensions. But if instead you have, say, 1,000 two-dimensional tables, that's possible. That's very much manageable. So basically, the idea is that if you want function that in practice can be dealt with, they need to be compositional. And as I said, that's a work in progress. But this would be a reason to say that the assumption of compositionality, which I think is necessary to try to understand why deep networks, including transformers, work, this assumption is an assumption about the word, and it's likely to be true in most cases. Thank you.
Thank you. Thank you very much for this very inspiring talk. Is there any question? Vladik?
Thank you very much for the very interesting talk. So just to clarify, 2 questions. One, do I understand correctly that if a function is time polynomial computable, it automatically has that limitation on the space? Or not necessarily?
Yeah, I think so. Yes.
Okay. And second, do I understand you correctly that in just normal least squares, is a particular case of what you said, if you...
As well as on the back, nobody listens to you.
Sorry. Okay. So
Maybe you can repeat.
yeah. So the first question was, if a function is time polynomial computable, does it automatically satisfy the restriction on the space? And the answer was yes. And second is on the normal least squares. So if you just instead of explicitly solving linear equation, use gradient descent, then in case of overestimation, you don't just get a solution, you get the solution with the smallest minimal norm, right? And which norm is that, 2 or?
L2.
L2, okay, very interesting, thank you very much.
Yeah, yeah. Just to thank you for the question. To complete the last statement, in linear least square, you are alluding to it. It's well known that if you have an underdetermined system of equations, you have more unknowns than number of equations. Then there are an infinite number of solutions. One solution that is usually used is the pseudo-inverse, which is among all the inverses, the one with minimum L2 norm. And it's also known that gradient descent, properly initialized, so with 0 initialization, and or with a regularization term, weight decay, will converge to the pseudo-inverse, so the minimum norm inverse. So what I'm saying is essentially the same thing for the nonlinear situation, where the norm now is not the norm is the product of the norms of the weight matrices. And yes.
Thank you. Any other question or comment? David?
So thank you very much for your talk. I have a more general question related to AI and superintelligence and so on and so forth. Listening to your talk, I tend to confirm my idea that there is nothing intelligent in machine learning. But what is your opinion? I mean something emergent.
Yeah, it's an interesting question. I tend to agree with you. We are still far from intelligence. But, for the first time, I asked myself, when looking at a conversation with a transformer, because you can have a kind of conversation with these large language models, I asked myself, if a transformer at some point becomes conscious, how will we notice? These machines are impressive. You can ask questions to answer in English. You can ask to write a program and give instructions in English. And the machine will do a pretty good job if the program is, say, 1 page long, not a big system. They have been measured to be, for tasks like this, as good as an average human programmer, which is amazing. So the question is the following in my mind. These systems are very much, I think, like an associative memory. And I don't know if you know about associative memories, but there is an interesting story behind it. So holography was invented in the 50s. Dennis Gabor, whom I met once, got the Nobel Prize for it. In holography, one of the applications, you can create an holographic memory in which you store at the time on a photographic plate the interference of the laser light reflected from an object, say a face, your face, say, and together with the laser reflected from ground glass, so noise-like pattern. And you can then superimpose several of these pairs on an hologram, and then retrieve each one of the faces when you shine the same noise-like structure that you have associated before to that particular face, okay? So this is like a neural network. You train on X1, Y1, X2, Y2, and then by presenting X2, you retrieve Y2. But at the time, the emphasis was on memory, not generalization, okay? And David Wishaw And Christopher Longe-Higgins published a paper, I think in '69 in Nature, in which they had a network version of this holographic process. And this network, especially when used in a recursive way, you get an output and you put it back as an input and several times, is very much like dense, deep networks of today. So back in the 60s. All right, so I wrote a paper in the 80s in which I asked whether essentially associative memories could explain how the brain works. I think associative memory is with the ability to generalize, so you may give a reasonable output even if your input is not one of the elements in the training set, but close to one of them or some of them. Okay, so this, I think a lot of what our intelligence is associative memory. The question is whether all of it is associative memory. I don't believe that, right? But I think that if you think of transformers like very large associative memories, they do an amazing job, I'm surprised, about the language. You can give hints about the story, the beginning of it, maybe the middle of it, the end of it, and then fill in between something very reasonable, like a person. There is a company, another company started by my friend Amnon Sashua called A21 Lab. You can install an app they have on your browser. It's called something like Nice Text or something like this. I'm forgetting now. You can check, and this app will do the following. You have to write a letter. You write your letter, and then you ask the app, I want a letter to be more friendly, a bit shorter, and it will produce it. And it does a very good editor job. So they're doing quite a lot of what we think is human intelligence. And so the question is, what is missing? I'm sure that something is missing. And the big question is what is missing something small or something really big? I don't know.
Thank you.
Just to continue on this point, I see that you don't mention the consciousness of artificial beings. So I'm not sure if you know the French pioneer in artificial intelligence, whose name is Jacques Pitrat. He has written a book on artificial beings, and he claims that artificial beings are conscious, but the definition of consciousness is of course different from the one for natural beings, but it exists, and he claims that it's possible to have artificial beings who are conscious of what they do, but he was not working with deep learning, he was working with strong artificial intelligence. So what do you think of this?
Yeah, there is a problem of consciousness. One of actually was my first graduate student was, let me see. Oops. Okay, top right is Christoph Koch, and he has become an expert in consciousness. So many years ago, I told him he should not work on consciousness before he gets tenure, but he did work on consciousness and got tenure, so that's fine. And he claims, with Giulio Tononi, a co-workers of him, that they have a theory called phi. They claim that there is some amount of phi essentially in every living being, and it's just a quantity how large phi consciousness is, which is different between, say, dogs and us. I think if you ask him, he would also say that probably computers cannot be conscious. I'm not exactly sure why. But so there are many. The point is there are many ideas about consciousness. I don't know. For me, consciousness is a key part of it is being self-aware, and I wonder whether a transformer not trained to it could pass the mirror test. You know what the mirror test is? You know what you can do with a baby or with animals. A baby at about 1 year age can realize, looking at itself in the mirror, that is him, I'm me, this realization. It seems that a few animals, maybe elephants, chimps, can do that. So, you know, it would be an interesting experiment with the transformer. Give him an embedding in a robot hand, maybe simulated or so, and then try to have this test. But you're not supposed to train it on it or give him internet training that may mention that. So.
Thank you. Any other question or comment? Yes? Go ahead.
Okay, thank you for the interesting talk. So my question is, it seems that neuroscience could inform us quite well about like perception and maybe this RL, reinforcement learning, but it seems that there is a lot of other things, including reasoning, planning, and maybe counterfactual reasoning, which it seems that neuroscience cannot give us any clue how we are doing these things. So am I right that we are very far away from the point where we will be informed by neuroscience how we can simulate these high-level processes?
Again, I tend to agree with you, but you know, there are papers, one of them very recently on a very large transformer, showing examples where it does planning, not even just that. It explains you what a joke, a specific joke. It explains you why it's a joke and you know what it means, and very impressive. Now, you never know for those things whether this is something that completely or partially was written already on the internet. You know, these machines are trained with basically everything that is found around. So there are questions of this type, but if you look at some of the examples, pretty impressive, both exactly on the things you said. I tend to believe that it's more like a memory, and there are many examples where transformers do ridiculous things because by changing the question slightly, you get them to say the opposite of what they just said before, as they really don't understand what they have been saying. But the jury is open.
Thank you.
Thank you. Thanks for your talk. I have a question also related to neuroscience. So with neural networks, we know how to mimic the architecture of how information is being passed to find some optimal outcome. But stochastic gradient descent as an algorithm for setting the weights seems so non-organic to me for how the brain seems to learn. What are your thoughts on that, and how much do we know how the brain learns?
Yes, very good point. I think I completely agree with you. I think several of the details of neural networks are not biologically plausible. For instance, representing a neuron with just an RLU is a big oversimplification of what a neuron does. But the learning part is the one which seems really not biological at all. With 99% probability, it's very unlikely that it is what the brain does. So I think that the one very interesting question is how the brain does learning in the sense of changing synaptic weights, which we know it's what is going on. Because that, in addition to tell us how the brain does it, it's to tell us also perhaps better way to learn than gradient descent. One possible direction is what I call layer-wise learning. So imagine that instead of doing gradient descent, so stochastic gradient descent in which you are trying to update the rules, the weights across the network at each iteration, you are freezing the weights in all the layers but one. And so you are training now just one layer of weights, and you are training to try to get the correct output. So this become a very local learning rule that very similar to a perceptron type rule, very similar to Hebb rule. So this could be much more biologically plausible. And there is some empirical evidence that if you do this, if you freeze all weights but one, and then you freeze that one and you unfreeze the top one and so on, and you recycle, you can get similar result to gradient descent. So that would be an hypothesis. It's also a prediction, because this would assume that synapses in the brain, say in the visual cortex, will become plastic in succession at different parts, like in V1 before V2 and V2 before V4 and so on. So it should be verifiable at some point. That's one way. I'm not saying it's the only one.
Thank you.
A last question? Here.
Thank you very much. You made an important statement at the beginning of your talk. That is, the problem of intelligence is as foundational as other problems, like the problem of understanding life or our universe. And we know that other disciplines, like, for example, biology, are studying these kind of problems too. But, for example, in genetic engineering, people arrived at, in principle, replicating human beings, animals or even human beings, and then they put a limit on the scientific community, put an ethical limit. We cannot replicate human beings because it is not a good thing. Now, my question is, do you think that we are arriving at the point of replicating human intelligence? And if this is the case, should we put a limit on the scientific research on this point?
Can you repeat the last question? Sorry.
Yes. Should we put a limit on our research in studying intelligence in order to avoid replicating human intelligence or even overtaking human intelligence in the same way genetic engineers are limiting themselves in replicating human beings?
Well, yes, that's a very interesting question about the dangers of AI. I think AI, machine learning, is a powerful technology, and as all powerful technologies, they are potentially very good and very bad. So I think it would be impossible to stop progress, even if we try. So that's the main argument. I think we have to try to direct it in a good direction and not a bad direction. But to answer your question, I think that at some point we may want to connect our brain to machines. That's one way not to be to become a relic of the past. Personally, I think that, in fact, there are an infinite number of forms of intelligence. I find the term intelligence is very vague. So, were computers in the 1950s, when they were able to compute integrals much better than the best human mathematician, were they more intelligent or not than humans? And that question has repeated itself with chess and Go and everything since then. I think a transformer is intelligent in a certain way. Human intelligence is one of the forms of intelligence. If we want to understand it, and we probably want, because that means understanding ourselves in a very deep way, we will need neuroscience. Engineers will find many useful forms of intelligence, but I don't think engineering will solve the problem of human intelligence. So, I'm just saying there are going to be a lot of useful intelligence technologies, and it's up to all of us to make sure that they are used for good and not bad ways.
Okay, thank you very much for your presentation, your interesting talk. Thanks for questions. It's time now to go to the last phase of the event. So just a minute. So it's time now to give the Campet Ferrier Award. The Campet Ferrier Award has been created in 1992, given to Lotfi Zadeh for the first time. It's given at each IPMU conference every other year. So it's my pleasure to present the Campet Ferrier Award this year to you. For your interdisciplinary achievements on human and machine intelligence. So I would like to say that Tommaso Poggio's research is at the crossroads of neuroscience and computer science, dedicated to the problems of intelligence between brains and computers. He has made contributions to learning theory, to the computational theory of vision, to the understanding of the fly's visual system, and to the biophysics of computation. His outstanding contributions are focused on computational neuroscience, which he contributed to establish in close collaboration with several physiology labs, trying to answer questions of how our visual system learns to see and recognize scenes and objects. He is one of the most cited computational neuroscientists, with pioneering contributions ranging from the biophysical and behavioral studies of the visual system to the computational analysis of vision and learning in humans and machines. His research is now focused on the mathematics of deep learning and on the computational neuroscience of the visual cortex. He also introduced an approach called regularization theory to computational vision, made key contributions to the biophysics of computation and to learning theory, and developed an influential model of recognition in the visual cortex. Tommaso Poggio, on behalf of the IPMU Executive Committee, I'm happy to present the 2022 Campet Ferrier Award to you.
Well, I'm very honored and humbled by receiving this prize in name of a great multidisciplinary scientist who focused on information theory, a prize that great scientists have received already from Daniel Kahneman to Arthur to Vladimir Vapnik, who really started statistical learning theory, the kind of things I mentioned this morning with generalization bounds. So I'm very honored. Thank you very much, Bernadette.